Recording, Michael.
Yep, we're all.
Thanks everyone for listening for this optional lecture today. I hope that you will find it interesting and informative. What I'm going to talk about is the harmonic balance method and how we use it for doing a nonlinear frequency domain analysis of ordinary differential equations. And let me see if my thing's working here. Okay, and the things I want to talk about today basically are harmonic balance basics, talk about the classical harmonic balance approach, and do a demonstration with Duffing's equation so you get a feel for how the methodology works. And then I just want to do a quick demo on a Python Jupyter notebook to show you how you can, if you have an ordinary differential equation that you're interested in applying the harmonic balance method to, you can use this as a template per se, and you can do some harmonic balance analysis on your own with your own ordinary differential equation. And then I want to talk about the approach that Professor Hall developed back in around 2000 that allowed us to apply a harmonic balance approach for non-analytic governing equations. And I'll get into what that entails, but basically it provides a way for using the harmonic balance method for things like CFD solvers, which is important for us who are doing aeroelasticity. And then I'll get into the how we apply that approach for computational fluid dynamics solvers. So here's some basics on the harmonic balance method itself. The harmonic balance method provides a frequency domain approach for solving nonlinear time-dependent unsteady differential equations. That's the first point. The key aspect of the harmonic balance method is that the solution must be time periodic with a fundamental frequency and possibly higher order harmonics of that fundamental frequency. So the solution must be of just a single fundamental frequency. If it's broadband or any sort of nature like that, or multiple frequencies, it won't work. It has to be of a single fundamental frequency and possibly higher order harmonics of that frequency. And this, of course, lends itself well to many aeroelasticity problems. Oops, I got here. Jumped here. Well, the solution is represented as basically a truncated Fourier series expansion. X of t is our solution that we're trying to determine. And here it just shows the equation for a conventional Fourier sine and cosine series expansion. And NH represents the number of harmonics that we retain in that expansion. And the harmonic balance basic method, basically what it does is it will, when you apply it, it will convert a time-dependent ordinary differential equation or system of differential equations into a system of nonlinear algebraic equations. So it converts differential equations to algebraic equations. However, the thing to keep in mind is those algebraic that you end up with can be still very difficult to solve because they can be highly nonlinear, and in many instances you have to use numerical techniques to solve those algebraic nonlinear systems of equations. But at least it reduces it from a differential equations to an algebraic equations. So just to quickly go over an example here, I'm going to present or show how it works for the Duffing's equation. And this equation, as you see here on the screen, this is the second order time-dependent differential equation. I'm assuming many of you probably have heard of Duffing's equations, maybe done some work with them. If not, but it's basically a conventional spring mass damper type of equation, and then you have a cubic nonlinearity term here that's multiplied by this coefficient beta term, and then in this case we have a forcing term here, this gamma times cosine omega t. And the first thing we do is we consider that the residual of the Duffian equation itself can be, it can also be expanded in a truncated Fourier series expansion. So the equation itself is considered as a Fourier series expansion, and then we want to set that to 0. And the balancing procedure is going to come out is where we do the substitution of the expansion of x of t into the solution, and then we balance the terms so that we can determine the coefficients of these R naught cosine term and RCN and RSN terms, which are the coefficients of the sine and cosine terms of the expansion of the residual of Duffian's equation. So again, we substitute in our expansion into the Duffian's equation, and then this will provide us with a system of differential or algebraic equations for the unknown coefficients of the expansion for x of t. So just to start off with, we'll consider, why did this thing go down? Okay, for Duffian's equation, what I'll show here, especially on the Python's notebook, is that this thing can just blow up really quick and get very complicated. And this is why symbolic mathematical tools are really handy. But first off, we'll just consider the case of a single harmonic for our solution here. And then we substitute that into Duffian's equation, residual. You can see that just with that single harmonic expansion of the solution, that we end up with quite a complex expression for the residual in terms of the expanded solution of the in terms of the Fourier coefficients. Now what we have to, we've got to go through and do the balancing procedure, because what you'll notice is that, you know, we have all these terms, sines and cosines, but we also have products of cosine squared and cosine cubed in terms like that, and we don't want those. We want things to be in terms of cosine omega t, cosine 2 omega t, 3 omega t, and so forth. So there's two brochures that you can go about to determine the residual coefficients. You can just do a brute force approach, where you go through and you have to manipulate all those squared and cubic terms of the cosine and sine functions. Or you can do an integration approach, which I'll show on the Python spreadsheet. And you basically take advantage of the orthogonal properties of the sine and cosine functions. But just to show the brute force approach, is that what we to do that is just out of the way here. You have to apply the following trig relations, in this case, trigonometric relations, half angle relations, in order to remove those cosine squared and cosine cubed terms, for instance. And this thing's just driving me crazy. So again, this thing would get out of the way here. Apologize. Trying to clear up some screen space with all the pictures of everybody here. Yeah, that's better. So what we end up with here, I'll go over this quickly. The first line here basically was what I showed on the previous chart, was when you had everything in terms of cosine squared and cosine cubed terms and so forth. And then the second equality here is when I've made the substitution of these trig relations back into the residual. But as you can see, it's still very complex. But if you then go through and collect everything, then you can end up with the coefficients here now in terms of, you have the 0th harmonic term here is the first line. The next line would be the term that is proportional cosine omega t. Then the next one is sine omega t. But as you can imagine, doing this brute force approach it's a lot of work to do by hand. But what you end up with, though, is these coefficients then of these terms represent now these algebraic system of equations for these unknown coefficients of your Fourier expansion. And then if you want to solve this problem, you would then use some sort of mathematical technique. In this case, it turns out it's a cubic equation, nonlinearity. You have to actually use a numerical technique to solve this equation, even though it's just one harmonic, to determine it. But the harmonic balance method at least gives you the governing equations that you'll be needing to solve for. And so, here again just shows what the brute force approximation gave you. And now, because we only used one harmonic, we have basically an equation. We only really are concerned about the first three terms here: the zeroth harmonic, the cosine omega t, and the sine omega t. They provide us with three equations for the three unknown coefficients: xc naught, xc1, and x sine s1. When you have these nonlinear equations that have like a high order term, you end up actually with extra equations. But when you end up wanting to solve it, you only have this basically this system of three equations here that you're dealing with. And the reason you get extra is just because it's a truncated. You've done a truncation of the actual full expansion, which would go to infinity. So as you keep more and more harmonics, you reduce the potential that you'll have some, what I would say, left over. Because when you do just one harmonic, it's not going to be perfect because it's just, you've only done one harmonic. It could be, the solution could be much more complex than just having one harmonic in it. So that's something to keep in mind. So the second approach is the integration approach, which is, it's easier in principle because you can use tools like Mathematica, Maple, and also this SymPy Python library to do the work for you. But basically, you use the orthogonal properties of the sine and cosine functions, and then you can compute directly these coefficients of your residual expansions using these formulas here, for instance. And you just plug them into your Mathematica or Maple script, what have you, and you can just solve directly for, or you could do it by hand if you're brave enough to do that. And again, you will end up with the same expressions then for these coefficient terms if you go through and do the analysis. So let me see here. I'll see if I can share this spreadsheet or this Python notebook. Here we go. Okay, so can you guys see the Python notebook on your screen now?
Yes.
Yes.
Okay. All right. So this is what Michael just emailed to everybody, so you guys can fiddle around with this on your own. It's a real simple script, and I encourage you to tweak it and try some differences out on it. But basically, what the first chunk of code here does, basically, it imports the SymPy library, which is Python version of Mathematica or Maple. And it's great because it's free and it's open source. It doesn't cost anything, and you can tweak it and modify it. So just run that real quick. And then the next set of lines is the code that will basically set up the governing equation. And I put in a couple examples here. I put in, well, the first, I'll just go over the code a little bit. Basically, the first set of lines is in SymPy, you've got to declare your variables with the following command: xt delta. It just tells SymPy that these are symbols that will be used for the equations that you're going to be dealing with. Then there's some special conditions I put on the frequency omega, and this helps during the integration procedure when you determine the residual coefficients. It just makes the integration come out a lot cleaner because you tell that omega is going to be positive and it's going to be finite and it's not going to be zero, so you don't get like a division by zero issue. And then the next thing is that x tells that x equals a function, says that, okay, x is the thing that we're going to be solving for. So it enables the x to be, you can take derivatives of it and so forth. And then the next line is basically just an equation, and it defines the Duffing residual that I had on the charts. And here, this is just the syntax you would use in SymPy to show that it's the second derivative plus delta times the first derivative of x of t, then alpha times x of t, which is the stiffness term, and then beta times the cubic nonlinearity, and then the forcing term, gamma cosine omega t. And so it's pretty simple, just set that up. And then as example that you can fiddle with, I also included van der Pol equation here. If you want to try that out, you would just uncomment out this line of code here. But then this is basically van der Pol's equation you could fiddle around with in that sense. And then I was also looking, if you go to the following website that I've got down here, it's a Wikipedia site, there's a list of nonlinear ordinary differential equations. I don't know if it's coming up on your screen now, but it's kind of a handy list. And there's some, you ever get interested, there's a whole bunch of interesting equations that you could look into possibly applying the harmonic balance method to. One of them caught my eye the other day was the Besant-Rayleigh-Plesset equation. It's basically a nonlinear equation that governs bubble dynamics, and it's given by this formula here, which is very nonlinear. But if anybody's interested in trying out for some other differential equations, there's a whole bunch of them that might be of interest. But anyway, back to the Python notebook. So the next thing, okay, so we run that chunk of code, and there's the output that gives us the Duffing's equation there, as you can see. And then the next set of code defines the Fourier series expansion for x of t. And I've included now multiple harmonics. So first thing you do is you find the variables that, these are the terms of our Fourier expansion. And here I've called them A0, A1, A2, B1, B2, and so forth. And I've included code where you can do 1, 2, or 3 harmonics. You can do as many harmonics as you want. And just for fun, maybe I'll go ahead and do 2 harmonics just to show you how this thing really blows up as you start using more harmonics. So, whoops. So I'll do the expansion there. So here's what, you just run this chunk of code. So there I've set up my expansion will be 2 harmonics instead of 1 in the previous charts. And then the next set of lines basically does the substitutes that expansion into the governing differential equation, and then we'll run that real quick. Now it's kind of, bear with me, it's a little bit slow, so because it gets big, but it should pop up here in just a second. The star means it's running. But I think you'll see here. So there, can you see that on your end now?
Yes.
Yep.
Yeah, so you can see it really blew up compared to what you saw before with just 1 harmonic. And if you do 3 harmonics, it becomes gargantuan. And so I'm gonna go ahead and run this one. I'm a little concerned because it might take a minute. Well, let me go back and just I'll let you guys fiddle with that on your, because again, I'm concerned it might take a minute or 2 to run that to solve for the thing. So let me go back up here. I'll just do 1 harmonic again. So again, there's the expansion now when we just use 1 harmonic. And then, so the next line of code is then this formula to solve for the 0th harmonic term of the residual coefficient. And it's just a formula of that integral that I showed on the previous chart. So just run that. And then, so boom, there's your 0th harmonic coefficient term. and then you can do the first harmonic. It should take just a second here to run it. I think the one thing with SymPy compared to Mathematic and Maple is it seems a lot slower in my experience. But you know, you can't complain too much because it is free. See if it should pop up here in just a second. Yeah, there it is. So there's the expansion for the first coefficient for the cosine first harmonic term, and then I'll hold off on doing the sine term. But again, I just thought I'd show this Python template here. So if you guys are interested, you know, you can kind of tweak it on your own and fiddle with it. And if you get real fancy, what you can then do is SymPy has a whole bunch of solvers involved in it, where then you can, once you have these equations for your coefficients set up, you can use some SymPy code then to try to solve for the coefficients. But again, you typically have to use a numerical technique to solve for it, even for something simple as seemingly as simple as the Duffing's equation. All right, so let me go back to the presentation here. Okay, so all right, so now I want to talk about a more challenging case, and this is where the Duke harmonic balance approach that we developed about 20 years ago comes into play. And that is now we're dealing with a case where you have a governing equation that has a non-analytic nonlinearity. And one example of that would be, for example, a nonlinear spring with free play. And so what we'll do here again is we'll consider Duffing's equation, and to simplify things a bit, we'll neglect the cubic term, the nonlinearity term, and as well as the forcing term. And we'll say now, instead of the stiffness being just alpha times x of t, it's going to be a function, f of x of t. So our governing residual has this form here, and the stiffness term is now given by this function, where if the solution x is within a small region around 0, there's going to be no stiffness. That's the free play. And then as soon as you exceed that displacement, whether positive or negative, then the stiffness starts to kick in. So this is the way that the mathematical function for the spring with free play could be represented. And if you have a non-analytic sort of non-linearity like this, you can't do this substitution approach where you substitute in the expansion for x of t and then try to do the whole balancing procedure, because the function itself that defines the stiffness is a function of the solution itself, and you know, it has all these conditionals involved with it. And it turns out modern computational fluid dynamics solvers have these sort of similar features in them. With they'll have things like limiters for capturing shock waves. There'll be other things, perhaps they have these, like, they're called clamps in a lot of ways, that have these, they're just non-analytic sorts of features that you have to deal with. And so it makes it impossible to do just a brute force sort of harmonic balancing sort of procedure, what I showed at the beginning with the classical approach. So what is a way to get around that? Well, the way we can do that is that instead of trying to do a substitution of the expansion into this function f, which has this non-analytical behavior, is that we just go ahead and assume that the function f itself is a Fourier series expansion. Okay, we don't know yet what the coefficients are for this Fourier. This is now a new set of Fourier coefficients that we're going to have to solve for. But this is the first step. We assume that it can be expanded. It can itself be expanded in a Fourier series. And so if we go through then and we substitute now these expansion for both x of t and f and t to the governing equation, we end up with the following expression here. Here's the first line is just, we can the expression for the residual. And then the next line is where we substitute in the expansion into that residual. And here, we have our terms for this new expansion of the non-analytic function f of t. And then this is what we end up with then for the expansion once we, expand it out and take the derivative and so forth. And what we end up with then, and then to evaluate these coefficients, we again use the integration approach that I showed a few slides back. And when you do these antiderivatives, you then can end up with a system of equations for the zeroth harmonic, the nth, and the cosine n and the sine n terms that are given by these functions here. And you can express all that as a system of equations, okay? And so what happens is that you end up with a system of nt, which is 2 times the number of harmonics that you keep, equations, for the unknown coefficients x0, cn, and xnt that can be expressed as follows, as this equation here. And again, what this equation involves is x is now this x hat is these terms of the Fourier series coefficients, which are our unknowns, which we're trying to solve. This f hat is now the expansion of this non-analytic non-linearity function that we're dealing with. And then A is this matrix here that which I'll show, but it's a matrix that it's basically a pseudospectral representation of the time derivative ddt. The problem is that we can't really deal with this because we don't know what these Fourier coefficients for this non-analytic function are. So we need a way to get around that. And this is where Professor Hall had the clever observation that instead of dealing with the solution in terms of these Fourier coefficients, we can deal with the solution in terms of subtime levels. Okay? So rather than work in terms of the Fourier coefficient variables, which I showed on the previous slide, x hat and f hat, we can instead work in terms of the solution and this nonlinear analytic term evaluated at subtime levels evaluated over a period of oscillation. And this is much more easy to deal with, particularly for this f term here, because all this requires us to do is just to evaluate f, with our solver. We just plug in whatever t that or x and t that we're dealing with, and we can immediately compute that. If we're trying to deal with Fourier coefficients, we don't know them and we don't have a way to compute them. But if we're dealing with subtime levels, we can just plug it into our solver, our CFD solver method, what have you, and we can explicitly just compute these terms. And it turns out is that you can relate these two quantities, the Fourier coefficients, to the subtime levels via a constant Fourier transformation matrix, E here, which we call it, which is given as follows. And it would take, this would be almost a lecture in itself to go through how to derive this, but it's, just take my word for it. There's an explicit relation that directly relates those two sets of variables to one another. And when you deal with the variables in terms of the subtime levels, it makes life so much easier. So back to, this was equation, our governing equation when we were working in terms of Fourier coefficients with the hats here, okay? And then what we do is we introduce this new matrix called D, which is the inverse of E times A times E, the matrix. And D is also referred to as the pseudospectral operator method matrix that represents the time derivative term ddt. And we apply some transformations. I won't get into all the math of it. But basically what we can do is we can rewrite this original governing equation, which is in terms of the Fourier coefficients, now in terms of a governing equation that involves the subtime levels, okay? And this is infinitely more simpler to deal with, again, because we can just call or just compute explicitly these terms to set up these vectors. We don't have to know the coefficients in advance, and so they're easy to evaluate. And so what we do to solve this system then of equations is we will just typically pseudo time march this governing equation to determine the solution for the unknown vector x here, the subtime level solutions, by adding this pseudo time derivative term, and we just and tau just represents a pseudo time variable, and we will just march that solution to convergence, and that's how we then determine the solution for these subtime level solutions. And then we can then inverse Fourier transform to compute back to then the frequency domain results, which we might want to deal with. So that just gives you the gist, hopefully, of the idea of how we apply the harmonic balance method for cases where we're dealing with non-analytic functions where we can't use the classical harmonic balance approach. And the genius behind what Professor Hall discovered or came up with was this idea of reverting to working in terms of subtime level variables instead of Fourier coefficient variables, because then it just makes life so much easier, and it makes it also very easy to implement the methodology as sort of a wrapper around existing flow solver methods. Which I'll talk about now in the case of a CFD solver. So the concept is just the same for a CFD solver. And with a CFD solver, you can the residual for the CFD solver can typically be expressed in an equation that looks like the following. And here now the L and the J subscripts represent, the L and the J subscripts represent, we would represent the variable and the mesh point, because in a CFD solver, you're solving for multiple variables, whether it be density, momentum components, energy, turbulence model quantity, and so forth. So that's what the L subscript represents. The J subscript represents the mesh point. You got millions of mesh points perhaps, but at the end of the day, the residual can be expressed as the following ordinary differential equation. And then the idea is just the same. We expand both the solution, Q here is the solution, and then N represents the residual of the residual operator of the CFD method itself. And again, this is where the term that could be very highly nonlinear and have non-analytic sorts of functions in it with shock capturing techniques and limiters and those sorts of features. And The idea is just the same. We inverse Fourier, we do the substitution, then inverse Fourier transform. We end up with a system of equations that are in terms of the Fourier coefficients, but we don't want to deal with those because we don't know how to evaluate those directly. So what we do instead is we revert to the solution and then also the CFD operator itself evaluated at subtime levels within a period of oscillation. And we use the transformations that we showed on the previous charts. And then we end up with this now of a governing equation in terms of subtime levels, which is much more easier to evaluate. And we march this solution as with just a simple scalar case in Duffing's equation by adding a pseudo time marching term where tau is the pseudo time variable, and we just march that solution to convergence. So that's kind of a quick summary, or hopefully give you a gist of the idea of how we apply the harmonic balance method to a CFD solver method. And so again, the idea that I worked on this, and another student of Professor Hall's, Bill Clark, worked on this, and we presented the paper back in 2002. And again, it provides a method for solving nonlinear methods for time periodic unsteady flows. It lends itself to, the method now lends itself for CFD methods to problems where the unsteady frequency is known in advance. And so the harmonic balance method, when we originally developed it, very much lent itself to turbomachinery problems. For example, for flutter analysis in turbomachinery, or inlet distortion analysis, because there you know the frequency. It's not an unknown. And so, for example, we used it for solving for, this was transonic, these are some Mach contours for transonic turbo rotor configuration. And then we use the method to compute the imaginary moment is proportional to basically the unsteady aerodynamic damping. And then we could compute it with the harmonic balance method for various interblade phase angles. And so then what Professor Dow and I have been working on for several years is applying the method for general aeroelasticity problems. And there the challenge is, the problem is with general aeroelasticity problems, we don't know the frequency in advance. So part of the aeroelastic solution process involving the harmonic balance method is that in addition to solving the harmonic balance system of equations, we've also got to determine the frequency. And so we've developed some techniques. One of the original ones that we developed clear back around the time we did the original harmonic balance method was involving a Runge-Kutta technique. And I won't get into all the details of it, but over the years, we've applied it to a number of different problems. For instance, cylinder shedding and cross flow, two-dimensional transphonic airfoil configurations, determining the limit cycle oscillation behavior of those configurations. And then we've also computed for full 3D configurations like the F-16 and computing its limit cycle oscillation approach. But these are, what I want to stress here is that the general aeroelasticity problems is more challenging because we have to also solve for the frequency as part of the process of the solution. And we're continuing to work on methods to improve that process. So that basically was what I was going to share with you today. I hope I didn't go too fast or scare you away. Is there any questions or?
I have a question, Jeff.
Sure.
You've got nonlinear equations, so in principle, you could have multiple solutions.
That's right.
So tell us about that part.
Where to start? Well, a lot of times you get multiple solutions, and for like example with the Duffing's equation, what you can end up with oftentimes is, again, I don't have it here in front of me, but you'll end up with a solution that ends up being complex valued.
Uh-huh.
And so that obviously doesn't make sense. So that's like a spurious non-physical solution. So
Right.
when you solve for it, you're going to want, because your original assumption is that the solution was in terms of a standard Fourier sine and cosine function which are real valued. So if you end up with a solution that has complex values, that tells you those are no good. And but there are cases where you can end up with multiple real valued solutions, and then you're just going to have to use some common engineering common sense to get in and see what seems physical or not. And so yeah, that's an issue. You're right. You're exactly right, because you're dealing with non-linear algebraic equations, which of course will have multiple roots. And so yeah, that's part of the process. And so when you're solving these nonlinear algebraic systems, one thing that's useful to do, and particularly when you're doing like for a large many degree of freedom systems, is to start near where you think the final solution is going to be, because your solver, like if you're using a Newton-Raphson technique, then the Newton-Raphson solver will home in towards the physical solution and not a spurious one. So that would be the way I would explain that. But yeah, there's all sorts of interesting mathematical, stuff that can happen for these nonlinear systems.
Very good. Thank you.
Sure.
Jeff, I have a question. This is Michael.
Sure.
So I'll call them more conventional CFD approaches have a well-known sensitivity to things like temporal resolution, which turbulence model is employed, that kind of stuff. Do you see, and you said that those kinds of, turbulence models and subgrid scale modeling and those kinds of things are still implemented if you use a harmonic balance approach in a CFD technique. Do you see a change in sensitivity to things like resolution and turbulence model when you use this approach as opposed to a more conventional approach?
No, I don't think so. I mean, you're still going to get okay, I'm thinking like a Spaulding to Mars turbulence model, for instance. And in the Spaulding to Mars turbulence model, it computes all sorts of spatial gradients, because it's computing like vorticity and things like that.
Yep.
And those things will not be affected by when you employ the temporal harmonic balance methodology. And I'm thinking, if you're concerned though, if there is a temporal effect, well, you can resolve it just by, using more and more harmonics. Because as you employ more and more harmonics, you're building up the solution at more and more subtime levels over a period of oscillation. Does that make sense?
Mm-hmm, mm-hmm.
So you're gonna be getting higher resolution temporally, and also the nice thing about the harmonic balance approach is that it's spectral. It's going to have spectral convergence compared to like a finite difference method, mm-hmm. because it's a spectral technique, and so the convergence is going to be, the order of accuracy is going to be proportional to the number of harmonics you use, rather than any sort of delta time step.
Sure. So
which you would run into, and so actually it's probably going to be, the harmonic balance method is going to be better than when you do just conventional time marching, time stepping techniques, because there you're just doing basically finite differencing in time, if that makes sense.
Sure. So there's no real equivalent to a CFL number using harmonic balance.
No.
Yeah.
No.
Yeah.
Right. Well, okay.
Other than the fact that you need to, resolve a certain temporal scale for the dynamics to be captured. But in terms of stability, in terms of numerical stability.
Yeah.
Yeah.
Right. You're going to have some time scale which you're trying to resolve. And it's going to be related to that frequency that you're trying to capture, whatever the frequency is specified. So, yeah, I think that's the way to look at it at that perspective. Well, thanks, guys. If there's any other questions, let me know. And
sorry, Dr. Thomas, I had just like one more question.
Sure.
I was wondering, like, how, if you can give me like an order of magnitude of like how long like did it take you and Dr. Hall and whoever worked on that to build that up, like to kind of like implement this method, like
I'm trying to think back. It was kind of one of those like breakthrough moment things, if I remember correctly, because we were struggling with it for a while, and what we were trying to do was basically we were trying to do the brute force approach, and we were trying to do everything in terms of frequency domain variables, and it's just getting to be so complex, and then Professor Hall had this realization that, oh, wow, why don't we just work in terms of subtime levels, and then we can just use this transformation matrix. And then it was just like overnight, we had it. And it was, it was really quick after that. And that's another thing I should have mentioned is when you work in terms of subtime levels, is that it's real easy to implement the harmonic balance method within existing or computational fluid dynamics solvers. And I think that's probably why the method has gained so much notoriety over the years, is because it's extremely simple to implement. You can just look at your CFD solver as a black box, and then you just wrap this code around it, and then you end up with a harmonic balance solver. And so yeah, once we figured that out, it was just a matter of order weeks or months, and we were able to start producing these harmonic balance results with our flow solvers that we were dealing with at the time. But yeah, we struggled with it for I would say a couple of years. We were trying to fiddle with it, and we went so far as we were trying to use Maple and Mathematica to actually do these expansions of the of our CFD solvers at the time, and we were dealing with simple CFD solvers at the time that compared to the giant codes that are of the day, but we're still dealing with CFD solvers that had 3, 4, 5,000 lines of code, and we're trying to implement that, and substitute in a Fourier expansion directly into that. But it just became so cumbersome and challenging. So I mean, that's basically how it kind of panned out.
Okay, I see. Thank you.
Sure. All right, guys. Well, thanks again for listening in, and
well, thank you, Jeff. That was very good, very clear, and very helpful.
Okay. Well, there's a lot of math in that, and I apologize, but I mean, it's just I try to make it as concise as possible. But if you have any questions, do let me know. And
Michael, will you upload the presentation on Sakai?
I'll send the charts to Michael, and then he can send them all to you guys. So.
Okay, perfect. Thank you.
Michael, are you still there?
Yeah.
I don't know if he's still. Okay. Yeah, Mike, I'll send you the charts and you do what you
Yep.
need to do. With
Yeah,
it.
so I'm gonna put the slides up as well as the Jupyter notebook as well as a recording of this lecture. And I think
Super.
that concludes the meetings for this class for this semester, if I'm not mistaken.
Indeed,
Thank
it
you,
does.
Jeff.
Be
Sure.
safe, everyone.
Yeah. Hey, Earl.
Yes.
Earl, are you gonna listen into this aeroelastic prediction workshop that's starting in a few minutes?
No, I'm not. But if you are, please let me know what happens.
Okay. And then the other, I'm being zoomed to death.
Yes.
There's another one did you see the email at 1 p.m. There's going to be one for the Aviation 2020 conference. Did you get an email on that?
I did not. I don't know about that one.
Oh, wow. Yeah. They're going to have a town hall to discuss the,
I did see that. I'm
AV
sorry. You're right. I did see that.
yeah.
Now, what's the purpose of that? That's a pre-meeting meeting?